So good evening, anyone. We'll go ahead and get started. So for those of you who don't know me, my name is Lewis. I work here at Harvey Mudd as a sustainability manager. I've been here for about a year, and I work with the Hixon Center for Sustainable Environmental Design, which is the center on campus that sort of operates in three capacities. It's a bit of a research center, a bit of its own academic department, and a bit of its own Office of Sustainability. So we like to really spread our environmental reach across the campus in a variety of different ways, both academic and interpersonal. So we hope that our message reached you, so thank you for coming out, and we hope to see a few more people trickle in here. I wanted to briefly just talk about the Black, Gold, and Green series and what it's about, and then we'll go ahead and introduce our speaker for tonight. This is, I guess, officially the second go-around of the Black, Gold, and Green speaker series. We had something a little less structured last year, but we brought in a few speakers in for a few lunchtime talks. But this semester we wanted to sort of expand it a bit. We opened with a lunchtime talk with an old HMC alum who works for the Dow Chemical Company, Rich Helling. And this term we wanted to bring in a few evening speakers and really expand upon the larger environmental topics that are really at present big issues. So you'll see on our schedule, so not only did we bring in Dan, who I'll briefly introduce, but in a week or so, we're going to bring in a couple of folks from the High-Speed Rail Authority who will speak to the impact of the high-speed rail on the environment and sustainability issues that they have to consider as they go about constructing what is going to be a very large and time-consuming and financially burdensome mega project. A couple of weeks later, we're bringing in the Senate President Pro Tempore, Kevin De Leon, who is a Pitzer alum. He spoke at Pitzer actually last fall, and we were inspired to bring him in as well to talk about sort of how will California respond in the wake of an administration that isn't just as big of a fan on the environment as one would hope. So we'll get to bring him in, and we'll probably add another speaker in April. The whole point of this series is to sort of bring the sustainability issues big picture, especially because most of the time we're addressing them in these sort of case-by-case basis in the classroom. So we hope that you enjoy it and that you continue to come out to these. But I'll go ahead and introduce the speaker for tonight. When I first came here a year ago, I was pretty dead set on bringing Dan here. Dan was my thesis advisor back at Berkeley, and he also was a teacher of mine. And he was the guy who got me into energy, like wholesale. So that was the topic that finally got me to realize, oh yeah, this is the area I want to go into. So I felt, who better to bring in than not only a great teacher, but also one of the world's leading experts in this stuff. So he's a professor of energy and public policy at UC Berkeley. He has served as one of the primary advisors to the State Department and the Obama administration on climate and energy. And he has a really, really great talk to you tonight about the clean energy revolution and the state of renewable energy and climate change today. So without further ado, I'll introduce Dan Kammen.
Lewis, thanks so much. Well, I want to thank you all for coming out tonight, and I really want to thank Lewis. I'm a son of a historian, and I really appreciate it because when Lewis came to my office the first time, I really felt like I was getting a student who was sort of much more thoughtful and mature about understanding the history of technology and of evolution than my kind of typical style of operation is. As you'll see, we in my group, I don't want to say play fast and loose. That sounds really sort of informal, but we like to sort of do a certain kind of applied math and technical analysis and then kind of use it. And Lewis really said, let me go back and look at what have been the big transformations. And he looked at the German, very large scale, very important energy transformation and what are the lessons for California and a little bit of back and forth. And so I really appreciated having a student who kind of brought the kind of seriousness that you're supposed to have in a seminar class that I'm not sure my group always brings to the table because we like to be surgical and kind of move in quickly on topics that we think are really exciting at the moment. And that's actually what I'm going to try to talk about a little bit tonight. With all of the turmoil going on, not only in the US with our election, but in the UK, in Italy, in Colombia, there's been just large-scale political changes around the planet in the last few months to year. And where does this clean energy transformation, revolution sit in that story? And so I'll try to illustrate that. But like any good teacher, you always say that anything not covered in lecture will be adequately covered on the exam. And so I will definitely do that. And just to demonstrate, I've put back on the refreshment table, on the back table, kind of a small handouts for a journal that is now in its 10th year that I'm the editor for, called Environmental Research Letters. And it is really designed to be a journal that captures what I hope tonight's talk really embodies. And that is clean energy and the transition to that, successful or not, I hope it's successful and quickly, is highly interdisciplinary. And while I, as a physicist, and Harvey College with a strong engineering, natural, and physical science bent, have a huge role to play, I'm actually going to argue that the biggest thing I've learned since graduate school was the degree to which the science and technology is absolutely essential, but it is only a necessary but not sufficient condition to do what we need to do. And that places like Harvey Mudd, MIT, other places that really try to live the talk of being the place that trains not just the average really good engineer, but what they often call, and I've heard here called, the 100th engineer. The engineer who is exceptionally good at the technical part of the story, but really thinks hard about the broader social elements of the story. And so tonight's talk is going to point to the technical pieces. I think I have one equation in all the slides, but I'm really going to try to highlight the broader part of the story, recognizing that in conversation and question and answer, and if you go to the materials on the website, I'll show you in a second, the much more detailed analytic piece of that story is here. And I'm very glad to see we have some alumni of, I wouldn't say my primary department, that'll anger the others, but I came to Berkeley to be part of this thing called the Energy and Resources Group, a small unit founded before the OPEC, the oil crises in the early 70s, designed around the mission statement that I just described, designed around the idea that we need to be exceptionally good at our technical, scientific analysis, economic analysis, but we have to think beyond that from the beginning. And in fact, the faculty member whose slot I'm in, you never say you replace someone like that, but the faculty line that I came into when I moved to Berkeley is that was vacated by John Holdren, who has just ended his term as the longest-running science advisor to the president under the 8 years of the Obama administration. I'll try to do some justice to all of these kind of motivational features, but because the kind of work I'm going to describe takes so many different types of people and types of approaches, I'm just going to give a picture. This is one of our lab lunches. They go on every Wednesday. I think those are the groups who are there for the day. So it's a fairly large research group as a university-style team. And we have people working within my group on everything from large-scale, very, I don't want to call them traditional, but very optimization-based models of the power sector around the world. We have a whole team building a model called Switch. And this is a model that we use to look at the power sector in California, Kenya, China, Brazil, a whole number of countries. We also have a number of students and postdocs here that are working on much more technology-specific, trying to understand how the process of innovation and learning goes, down to some of the basic material science properties of batteries and solar cells, but also how the system works together. And then we have a number of kind of wild cards. This guy over here is running a program that's designed to look at clean energy as a tool for equity in relief camps and in very, very marginalized communities, Central America, South Sudan, and elsewhere. This is a research scholar from Honduras who is looking at the role of clean energy to reduce violence. There's a whole variety of what I would consider non-traditional uses of energy projects that we hope you'll get a feel for in the talk tonight. And for anyone who wants to get into more of the details, the website of the laboratory is designed to be self-evident. That's the Renewable Appropriate Energy Laboratory, Berkeley EDU. And the Twitter feed is not my vacation pictures or something. This is designed to be roughly 1 or 2 tweets a day about aspects of the work in the laboratory. And so I want to start off at the very highest level to think about the sustainability transition, but from the mindset that I hope that the title of the talk brought together. Are we in a moment where the transition from the energy economy we have today towards what we need in mid-century, roughly 80% or more decarbonized, is something that you take lots of little incremental steps, the evolution, or is it a revolution? And I'm going to talk for the first 10 minutes about a non-technical aspect of the story, something that I think we will look back on as a remarkably important transition in how we think about sustainability in terms of energy and water and other resources. And again, I'm hoping that this story encapsulates what I've been sort of trying to get at. And I'm going to start off with something that did not have a very hopeful beginning, and that is the international process to negotiate a climate treaty. As far as one could be from my background in physics, engineering, natural sciences in many degrees. But this is a process that began in the late 80s and was crystallized in the early 90s in the so-called COP series, the Conference of the Parties. The big conferences, probably the most well-known, was COP3 in Kyoto, when the Kyoto Protocol, that I'll describe briefly in a second, was hatched. And then the very unsuccessful climate conference in Copenhagen, the sort of the disaster of promising a lot and getting nothing done. And then the turning that whole story on its head just 2 years ago at the Paris Climate Conference that was wildly successful, without actually getting much done, but wildly successful nonetheless. And now the most recent meeting that just took place in November in Marrakesh. And then did anyone attend either the Paris Climate Conference, COP21, or COP22 in Marrakesh? This means that the faculty here need to get more of their students out to these things, because you really learn a lot by seeing it in operation. So from COP1 through COP20, we had a series of meetings that at best produced the Kyoto Protocol, and that was designed to slow the rate of warming such that the industrialized nations, essentially only Europe and Japan, there was a couple complicated outliers, agreed to collectively cut not their emissions, but the rate of increase by roughly 7%. And that was supposed to have taken place by 2010. It did not happen. We had a variety of features. The U.S. essentially never signed on. There was some hemming and hawing, but the U.S. had a resolution in the Senate under President Bush the first not to make progress on this. Any Canadians in the room? Okay, so I'm from Southern Canada, I'm from Ithaca, New York, so I'm from Southern Canada. But Canada signed on to the treaty and then discovered Alberta, and then had to back out because Alberta's emissions increase swamped all of Canada's, and so once you discover Alberta's actually part of Canada, you had to back out of the whole process. Russia was able to sign on because their economy was in free fall, and because all of these emissions targets are based on a baseline year, generally a baseline year before you begin reducing, so there can be an actual baseline. Russia, whose economy collapsed by roughly 90%, suddenly had 90% more emission credits than they were using because the economy collapsed, not because they were going green. And so they were able to sell those. And so Russian hot air was a popular tradable commodity at the time. Suffice it to say, this process led to nothing. Lots of big meetings, big dinners at these various meetings, but basically nothing came out of it. Kyoto Protocol that only applied to the industrialized nations, so-called Annex I nations, of which many backed out and some, like the U.S., never signed on to. China and India didn't sign on because so-called developing nations did not have any targets. And certain countries, I won't mention them, China and India, they routinely said we're a poor developing country when it comes to spending money, but we're a powerful, important country when it comes to setting the targets. And so, for a variety of reasons, nothing happened. All of that changed in 2014, not at one of these conferences. And it changed in 2014 because two of the countries throughout the entire political science process and said, we're going to stop having negotiations with 190 countries where one year Bolivia blocked things, another year Sudan blocked things, another year China, another US blocked things, and just the US and China are going to step out of the whole process, And this G2 summit of climate is going to move ahead and define its own highly unconventional treaty. And this is really the evolution or revolution. US and China, 40% of global energy consumption, 40% of emissions, basically said, it doesn't matter what anybody else does. If we come to a deal, everyone else in some form will have to sign on. Maybe they'll sign on by saying they actually thought of it, but basically they will have to go along with the deal. And so what President Obama and Premier Xi said is, we're going to strike a bargain on climate, and we're going to use that to pressure the international community. But at the same time, because neither one of us have internal agreement within our country, we're going to use this to try to leverage domestic action at the same time. So this is a complicated structure. And the deal that they struck, all my political science friends kind of threw their notebooks in the air because it didn't make any sense. What the US agreed to do, or the president agreed to do, was to have domestically a cut of 1/3 of our emissions by 2025, and didn't have any domestic agreement to do this, but that was the so-called Clean Power Plan. And Premier Xi said China will simply peak their emissions, not cut, but simply peak them 5 years later, 2030, and then maybe go down, but we'll see. The US cutting by 1/3 is certainly a nice step towards what we scientifically absolutely agree needs to be done, and that's an 80% reduction in emissions. If you read the fine print, what it actually says is an 80% reduction in emissions using the 1990 baseline before the Kyoto Protocol began. But that's a long time ago, and we didn't really do anything, and so, of course, our emissions were a lot higher than the 1990 baseline. So what the U.S. said very quietly on the side was that cut of 1/3, it's actually based on 2005. And every European country had a fit because they were all using 1990. How does the U.S. get to just redefine things? And China didn't say anything. They just said, we're going to peak emissions. Didn't say peak emissions at our current level, at 5 times the current level. Just said, we're going to peak and then come down. So this is a weird treaty in all kinds of ways, but I love it. And that treaty led to the French hosts in Paris getting to raise their arms and say, what a great deal. Of course, they may not be in power much longer since France is going in a very odd direction. The former UN Secretary General was elated. Of course, now he's running for president of Korea and not doing so well. Xi, head of the climate process, wanted his job, didn't get it. But they were all very happy this day in Paris during the meeting. And what were they happy about? And this is really where the connection between the kind of the science background, why, how I got into this field, how I hope many of the students are in this field, and the politics plays a really interesting story. This is the classic climate picture that gets drawn and redrawn 7,000 different ways. So, billion tons of emissions. This is the so-called business as usual, or some of us used to call Bush as usual back in those days. And this was to lead the world into 4, 5, 6 degrees or more of average global warming, and with a set of now fairly well understood dire consequences: dramatic change in ocean circulation, dramatic changes in forest fires, droughts, all manner of features of which you can always find someone in every crowd who wants to debate one feature. Maybe it's due to solar variation, maybe it's due to Martians beaming microwaves. There's always someone who has a theory for which they'll defend till the end, and no disrespect to those various views, the global science community says, you're dead wrong. The science is exceedingly compelling as to where we are on climate change. It's also exceedingly compelling as to if we don't achieve roughly this 80% or more decarbonization, the costs, social, economic, environmental, would be very high. There's lots of room to debate the details, but it's largely that. You are wasting your time debating small elements of a much bigger story. That said, where we are today is we have demonstrably raised the global average temperature by 1 degree. And so when we talk about having already done 1 degree onto a path of 4 or 5, where somewhere in this range, really catastrophic things, dramatic changes in the biogeochemical cycles happen, really severe, world-altering, dystopian future changes are almost sure to happen. Doesn't mean we can predict exactly which day. I got a letter from someone who's in prison just yesterday saying that Thanksgiving Day 2074 was going to be one of these critical tipping points, and we can discount kind of over accuracy, but lots of very clearly understood from the chemistry and the physics changes will happen if we remain on this path. What happened in Paris as a result of this US-China deal was that the traditional rules of negotiating a treaty, do the science, understand the impact, and then negotiate. That's how the Law of the Sea, the CITES Treaty on Biodiversity, Clean Air Act, all of those were versions of that process. This was the opposite. Many scientific agencies in the United States, in Europe, and elsewhere were shocked that the US and China came to this two-party deal, and they came to a deal where they explicitly said this 2-degree limit was going to be the goal. Not that either country's goal in 2025 for the US or 2030 was absolutely going to get there, but this goal of getting down to 2 degrees of ultimate climate change, only giving us 1 degree left of warming in our future, and that gives you a carbon budget, was the goal. When the US and China did this, 40% of the world emissions, every other country fell in line in an incredibly chaotic but interesting way. In the year between the US-China statement in 2014 and the climate conference, each country announced its own national climate plan, and those plans added up to roughly this pink triangle. The plans were incredibly diverse. It was very hard to compare one to another. The US and Chinese plans were very largely focused on cleaner electricity. The US taking advantage of low-cost gas, fracking with all of its complicated features, etc. China by becoming the world's largest manufacturer of solar panels and wind turbines and batteries for electric vehicles, and China just announced another step forward with a $360 billion investment in clean energy, largely in the wake of the potential large sucking sound for the older people in the audience of the US maybe pulling out of this process for things I'll mention in a second. Every other country came up with its plans, and when you added them all up, some were incredibly focused on electricity, some on transportation. A number of sub-Saharan African countries focused very hard on land use, conserving forests. It was a free-for-all. Whatever you wanted to propose was counted, and no one was turned away from this unconventional treaty. And those commitments, nothing had happened by Paris, these were all nice pieces of paper, added up to about a degree of cooling over the business-as-usual plan. And things even went a little further. Of course, you'll notice, that there's this large block of yet unrealized emissions, and there are really no plans for those yet. And this is a place where the science community failed politics, not the other way around, and I'll explain that in a second. Because there really weren't plans to get rid of this light blue or gray box here, but interesting things were happening along the way. For example, very quickly after the Paris Agreement, the so-called Kigali Accords were put into effect, and they basically cut off another half degree by focusing on HCFCs. And what's interesting is that when the Kyoto Protocol was passed in the early 90s, it took 7 years to get to the roughly 55% of global emissions, countries and their emissions agreeing to cut. Of course, many countries backed out. Canada and the US never signed on. But this treaty, these pink emissions here, in under 1 year, enough countries signed on so that this went into effect. It went into effect the day before Earth Day, 2016. Remarkably record pace, largely because anyone's plan was accepted. There was not some criteria, if you didn't cut X amount of electricity sector, you were out of the game. It was a very welcoming but very vague process. And then another half degree was cut off pretty rapidly and pretty quickly in the Kigali Accords, the last major deal that for the United States, Secretary Kerry signed. Interesting place. If you look back at these climate discussions over the years, when there was a major climate year coming up, like the Copenhagen Accord that didn't really work out very well, or didn't work out at all, there would be a big focus on electricity. And in the other years, there would be a big focus on poor countries. And they were never pulled together in the same conversation. And one of the features of that was that over the last 5 years, there's been a very clear recognition that with roughly 1.5 billion people off-grid without basic electricity today, and the prospects being terrible for the future. And so what you see in each pie chart here is the pie chart on the left is in millions, the number of rural people, the larger part, and the smaller part, urban people, without electricity today. So Latin America in a pretty good state of affairs overall. That's the current number, and that's the 2030 estimate. But India, roughly no change. China, the numbers are a little suspect, but we'll leave that aside. Southeast Asia, not so good. And Africa, the big loser in terms of the number of people who are expected to be without access in 2030. Meaning, we not only have a climate story, we have an equity access energy story, and that story is a pretty ugly one in terms of the number of people around the planet without energy. Well, one feature that was noticed, for good and bad, is that in many parts of the world, very, very inefficient and polluting liquid and solid fuels are the primary form of light. And so you get interesting and intriguing and sometimes misused statements like kerosene is a massive industry, $25 billion or more per year. So there's all of this money at the base of the pyramid. And that became a hugely popular topic, book after book. Every business school couldn't write books fast enough about how we're going to save the planet by basically making poor people pay for it, which sounds very worrying, because they're already paying for all of these very ugly and dangerous forms of lighting, so surely they'd buy cleaner sources. And that's an interesting piece of economics, recognizing the opportunities for the poor, but at the same time, if the rich are not making any progress, it really sounds bad that we're somehow going to save the planet by making the poor pay for it. Then, of course, the U.S. had a little election. Things have changed a little bit. No one's quite sure where we're going. It is a worrying story out there in terms of will there be significant investments at the Department of Energy, the Environmental Protection Agency. Many of the agencies over the last 8 years allowed President Obama to sign that deal with the Chinese, essentially to say, without having gone through the House and the Senate, that we have enough programs in place, many of which came out of the stimulus package in 2007, 8, 9. Remember, of the $800 million in the U.S. stimulus package, energy got the largest amount. Not so much for research, but energy efficiency, programs for deploying solar, a lot of efforts that jump-started the industry really trace back to that last stimulus package. It's, of course, interesting today that Mr. Trump is talking about $1 trillion package, and if similar money might go into clean energy or into the transition, there's interesting things out there. But, we are certainly at a state of affairs where the science community planning a march in Washington, D.C. for April 22nd. There is, of course, great uncertainty about where we're going. And why this is interesting is because President Obama never got his package through the House and the Senate. There was an effort in his first term for a climate bill, didn't work out, the Waxman-Markey bill, and not totally dissimilar in China. There's interest, there's an economic argument for clean energy, but neither leader really had the package put together. What's interesting about the U.S. plan under President Obama, the so-called Clean Power Plan, is that this is just a chart showing each of the U.S. states and showing their electricity mix. Some, of course, are essentially entirely coal-based. Others are almost entirely based on clean energy and gas. And the role of gas is probably the most interesting and complex part of the story, because while gas is certainly a fossil fuel, and we're exceedingly worried about a number of aspects of gas, fracking, the leakage of gas, a whole variety of things we might talk about in the question period, the way you use gas can either absolutely facilitate a transition to clean energy, taking advantage of large gas resources and very low cost today, or it can absolutely block that transition. Essentially, gas can be used to go from coal to gas and no further, or gas can be used to go from coal to gas to renewables. How that gets managed is exactly why that 99th engineer is so critically needed. Because How you design the research programs on new science, materials, policies, regulations, all of that critically determines whether gas gets used in the ways that we envision in California, so that gas backs up renewables and that gas projects built today acknowledge that they must be gone from the system in 2050. Or the kind of discussion about gas that we see in a lot of Europe, which is we have a goal for 2050, that 80% decarbonization, but all of our short-term policies are about switching over to gas or something else, and they actually block the long-term strategy. And you can argue because Europe's gas comes from Russia, which has not been a very successful partnership, whereas US gas comes domestically. There's lots of broader political story that scientists need to be aware of, but in many ways, it's the deep technical parts of the story that allow pictures like California's story here to be the really interesting opportunity. And so what you see here is California using its 1990, not its 2005 baseline, noting that, of course, energy emissions were rising. And so when California passed its climate law, Assembly Bill 32, authored by someone who I still think should be winning the Nobel Prize, the Peace Prize, Assemblywoman, now Senator Fran Pavley, California rose to about 20% over its 1990 baseline, and then passed a law that said we have to get back to our 2020 baseline, so get back to our 1990 baseline by 2020. So that's being true to the original spirit of the Kyoto Protocol. And from there, we then have to get to a 2030 mid-target, 2040, 2050. This is what's really interesting about what California has done, and it's why, in many ways, what California has put together as a package stands on its head lots of the conventional thinking. So just to be clear, California 2001, massive energy crisis, utilities going bankrupt, a disaster of sort of epic proportions in California. 10 years later, California, one of, if not the most important climate law in the world, and California, which missed its 2010 target, and that was to be 20% powered by renewable energy, is ahead of schedule and will exceed its 2020 target. And by essentially everyone's assessment, we will make our 2030 target. And what's interesting is that we have things in California like Pacific Gas and Electric saying we're going to close the last remaining nuclear power plant in the state, Diablo Canyon, early. And at the same time, we are going to voluntarily, with quotes around voluntarily, we are going to exceed the 50% renewable energy target in 2030 by 5%. That's their stated position. There is lots of room for skepticism about the details, but in a state that 30 years ago planned to have a nuclear power plant every 20 miles along our coastline, we're down to one today. And with a very different path, Germany, that is by far the leader of large industrial states in Europe, is essentially down, is on a path to get down to very low numbers of nuclear electricity use. Now, we all have our little dirty secrets. California is perfectly happy to import nuclear by wire from other states, just as Germany is happy to help finance nuclear power plants being built and coal plants being built in other countries and bring that energy in by wire. So no one is perfect in this story. But California's story in many ways relates back to something that came out of the planning back when PowerPoint was not a word, when this kind of graph was done by draftspeople in offices. This is the so-called Rosenfeld curve, designed by Art Rosenfeld, who just passed away, Enrico Fermi's last doctoral student, National Medal of Science winner, professor at Berkeley, director of the particle physics group at Lawrence Berkeley Lab, etc., where he said, trajectory of past growth, and then planned growth with nuclear, fossil, and hydro. By being more efficient, we can carve off this wedge here. Back then, they couldn't do color PowerPoints. But this should remind you a lot of the picture I showed you before about the 4.5-degree path in pink down to that middle line, and then the need to cut further. And I would argue that California's feeling that it could get this kind of thing done was largely due to the fact that Art was right and essentially every large-scale energy analyst was wrong. Everyone else said, no, you want to grow the economy. We know that energy generation must track with GDP. And so all of the major groups, both from the oil and gas industry, major think tanks, all plotted, if you want to grow the economy like we're doing, you have to grow large-scale energy sources. Art said, nope. Energy efficiency saves you money, it allows you to be smarter, and cutting off these triangles, or wedges as they're called, became the law of the land. That interesting story led to pictures like this. Every Californian politician, whether they like this or not, has seen and argued about versions of this picture. So if this large box here is the amount of emissions California would have done its business as usual inventory in 2050, an 80% reduction leaves you only this box here. And the reason why I show this schematic picture is that we have a huge range of wonderfully innovating and innovative technologies in the solar sector, in storage, all kinds of things. But as I said in the beginning, I have come to believe very strongly over my career that the science and technology is the necessary substrate, but it does not define the process. What's interesting here is that the range of politicians, the range of people with very disparate views, people who are adamant pro-nuclear, pro-solar, pro-this, pro-that, all understand this picture. And what it says is that California's strategy today is to do two things. We have two axes here. Greenhouse gas intensity, how polluting a fuel is. Generally, we put coal as the most polluting, although not always. And then natural gas, and then renewables, because we're doing a life cycle or cradle-to-grave analysis. And so we can choose to develop technologies and policies that allow us to go to cleaner fuels. And then there's the mixture of liquid fuels, both fossil and biofuel, and electricity. And California has made a bet on electricity over liquid fuels, over petroleum, diesel, and biofuels. And that's different than 10 years ago when we had quite a different bet. So what that's saying is that our box of ultimate emissions is going to be crushed down from the top and shifted as far over toward electricity as we can. And I'll leave a discussion of hydrogen, where that fits in or not. I mean, of course, technically it's a gas, and so we'll talk about that one later on. But this box has meant that every time a new bill comes up, legislators that like it, don't like it, are able to have at least an intelligent conversation. And that's not true everywhere. At the federal level, for example, the reason why President Obama could not advance his plan further was because everything in the federal plan hinged on one thing. And that one thing was the Supreme Court finding that carbon dioxide at enhanced levels from human activity was a pollutant. Everything that was passed relied on that. And that meant that it was incredibly fragile. In fact, we know from Mr. Trump's plans, or at least plans before last night's more inclusive speech, was to go after directly that Supreme Court finding. And the succession of Supreme Court appointees is going to have a key role in how empowered or how gutted the federal infrastructure is. Now, I remember I mentioned all of the stimulus spending under President Obama in the early years that enabled us to think about these cleaner technologies because we invested a great deal in solar. We have a wonderfully successful program on making solar power more available and cheaper. It's called Sunshot. And I love the idea of having a federal ruling that another country gets done for you. Let me explain. The Department of Energy runs a program called Sunshot, and it says solar power should, from large central facilities, should be $1 a watt, or roughly 10 cents per kilowatt hour by 2020, and that rooftop residential should be $1.50 or 15 cents per kilowatt hour, roughly, by 2020. And 1 month ago, the Department of Energy announced success. That the federal government had met its plan, and it's met it early. This is 2017, so we're meeting our target several years early. And what's interesting, of course, is that we didn't really do it. This is the quasi-economic but widely used learning curve. Probably the most frequently utilized tool to think about the mixture of investment in research, in materials and other issues, and the economics of programs. And I'm hoping everyone has seen some version of this. This is effectively a version of Moore's Law. What you see here, which I don't have to explain in this audience, but everywhere else I spend 10 minutes on, is that this is a log-log plot, and time is just a stamp along the curve. It is neither axis. Each of these, whoa, sorry about that, got a little too excited. Each of these dots along here are critically important innovations. Some in materials, some in processing, some in handling. Each of these made someone a lot of money or some company a lot of money, but in this log-log space, they look like a series of necessary innovations along the way to bringing solar down to a price that 10 years ago, essentially no one thought it would be at. There are people who are going after the fact and saying, oh, I really predicted it back then, but really nobody did. We are down here now. Solar is now directly competitive with fossil fuels, something that is a remarkable piece of progress, and we debate endlessly about subsidies and this and that. Are solar more subsidized in some places than others? Yes and no. What is the most subsidized energy technology in the world today? It is petroleum by far. But what is interesting in this process is that the U.S. met this sunshot target because China ramped up production massively and learned by doing and moved us down along this curve. And so it's a great step forward. And just to see how remarkably far things have come, Dubai announced a series of calls for large-scale solar projects. This is a large-scale thermal project like the Ivanpah project on the Nevada border, a technology which 10 years ago almost everyone thought would be the dominant solar technology for a variety of interesting reasons, largely because it integrates storage, but because solar has gone so incredibly rapidly, we now have projects coming in unsubsidized at under 3 cents per kilowatt hour. Remarkable progress. Now, in this case, there was not a lot of demand for this piece of land here, and so there's actually no rental fee for the land, but many of our rooftops in California and elsewhere are effectively providing rent-free land. There's a whole interesting story behind these technologies. But here is a price number. This is kind of the MC Hammer moment. This is, you can't touch this. I mean, there's no project done anywhere in the world at this scale, energy-wise, that competes with this price. Not nuclear, not hydro, not gas. This is the cheapest, and it's solar. 10 years ago, seen as the most expensive. Fascinating interplay. Lots of interesting science to do there. And if we look at the world's 4 leading solar countries, I'm just plotting the gigawatts deployed in each country, and in the little polar plots, that's really what I want you to focus your attention on, I'm showing each country's role in the global photovoltaic industry in 2000 and 2010. Let's start with China, basically not a player in either one, but today, a massive leader in manufacturing, some share in patenting along this axis, and some share in market. Japan really got the global story started by an incredibly thoughtful program of basic science and then deployment science. And so in 2000, Japan was a major player in market share and in manufacturing, not such a big element in the innovation, the patenting side. Today, much more balanced, but a much smaller share because many countries have eclipsed it. Germany had the highest profile program for many years, became a major innovator, and then became a major market player. And slower, but with huge potential, the United States, a big innovator, still a big innovator, and with places like California and New Jersey and others playing a big role, ramping up kind of in a dramatic way. And so we're seeing a really interesting and complex interplay of material science, basic technology research, and this global, a global economy of renewables. In fact, many people are already pointing to 2012 as a year we'll look back on as an incredibly important year for solar. I don't think I marked 2012 on the graph here directly. My apologies if I didn't. Yeah, it comes around here where this dip was actually. 2012 was the year that global semiconductor production switched over from being the majority of it for computers to the majority of it for solar panels. as an interesting landmark in kind of the shift in scale of technology. I won't go into the details because I'm running a bit late, but the kind of studies that we're now seeing, this is a retrospective look back at the Japanese program. Research dollars are above the axis in these various shades of green and not whatever that color is there. And so you see the Japanese program, this is in billions of yen, started with a lot of research, ramped up slowly, and then had a delayed program that invested in deployment. And so you get some really thoughtful efforts. Rarely do you see this kind of careful thinking about timing and scale, but it's a really interesting part of the story. And so here is, for example, U.S. investment. We have President Carter ramping up energy research, but notice the biggest part of the ramp up here was actually work on fossil technologies and some work on hydrogen and other things. And so here we have this interesting mix, and then we had, with the oil prices falling under both Democratic and Republican presidents, our energy R&D budget was actually smaller than our national research program on pet food. Not a great sign. But then under President Obama, we got a remarkable scale up here. And again, if you look closely, you'll notice that actually fossil got the largest chunk of that increase. This was designed to so-called capture carbon from fossil projects. And at least the good news so far, we will see what the new budgets look like, is that while it's not at the level of these peak levels, at least up until recently, the budget levels have been higher than before. And we know from a whole variety of data that I won't talk about in detail, we have lots of graphs to talk about it, that there's lots and lots of interesting learning and innovation in this area. So I want to conclude by thinking about what does it now mean to kind of be that 100th engineer and to kind of put together pictures of these systems. So my laboratory and many others are quite active in thinking about the energy mix that we're going to need to meet these climate targets, and what does it mean in terms of planning and integration of new advances in all of these areas, in advanced batteries, in flow batteries, in flywheels, in building integrated solar, in geothermal, and a whole variety of technologies, and the use of conventional fossil fuel systems. And so to do this, my laboratory is active in modeling different regions. We're one of the groups that builds models that all of the states in the WEC, the Western Electricity Coordinating Council, use for their planning. We also have teams that I won't talk about here, again, working in 3 Central American countries, in China, in Kenya, and elsewhere. But I'll focus the comments here on the WEC. And Alberta and British Columbia are observers. They're not actually directly participants in the market issues. And little bits of Mexico are involved as well, and that'll become important in a bit. So the model results I'll show you are actually for the energy future in the WEC, which is dominated by California. About a third of all the energy used in this area is used by California. We have some linear programming tools that we use to plan out the system. I will not go into the details about how we do the math for it. But what I will show you are a variety of results in thinking about scenarios that get us to those low carbon targets. And this is I'm going to conclude with my opening comment, and that was largely that the science and technology base is critical. We need to keep innovating on it, but actually the decision making is much more important than the hardware. Let me try to illustrate that. So what I won't describe here in our modeling efforts, we have a large set of linear program that we use to look at the deployment of not just energy generation, but also energy efficiency and the construction of transmission systems and distribution systems. And all of that is available. What did I just do? Something strange. All of that we use not to know what the answer is, but to try to understand the interplay of different technologies. So what I'll show you will be a bunch of stacked bar graphs of the energy mix for different types of scenarios that kind of make sense with the West getting to that 2050 goal of a decarbonized world. And this will, I think, hope to sort of bring together a lot of things that will make sense in terms of what our options are. So just to give it, what I've done is I've taken a snapshot each decade from 2020 up into 2050, and what this modeling program switch does is to meet the climate target for the least overall cost. So this model meets energy demand with supply and puts energy into storage, and it does so by investing money every 24 months in new technologies and policies. So the height of the bars grows over time because, of course, the energy demand is expected to rise. And the leftmost bar is the reference scenario. That's just using the expected price declines for the technologies, the so-called learning curve I showed you all before. And here are a whole bunch of scenarios that myself, the Governor Brown, various people who we interact with have asked us to build. As an example, here's a scenario called limited hydro, requested by the governor's office, and that says that because of the multiple demands on water and the fact that we are basically stealing water from our neighbors, California should have a plan to reduce our dependence on hydropower by 50% by 2050. It doesn't say less flow in the rivers. It says using less and less of that water for electricity generation so we can spare it for other purposes like farms and nature and various little things like that. And a scenario that I talked to you about before is sunshot. If solar becomes cheap, that's the second bar here. Well, you'll notice, and hopefully the colors kind of make sense with photovoltaics, and orange is solar thermal, meaning solar plus some storage. Here's 6 hours of storage built in, like the Ivanpah facility. But if solar gets cheap alone, it doesn't dramatically change that much. But if solar gets cheap and batteries get cheap, this is my favorite, it's also the governor's favorite, scenario right here, this one really does transform. And this is the one that I'm most excited on myself, but other people like other scenarios. So for example, this one where nuclear becomes cheap and so does carbon capture. Here is one that there's a number of advocates for. And as I was building the model, I learned that it was computing things accurately because when I first ran the model, I put in all of the various constraints. California has said it's illegal to build any new nuclear until we know how to manage the waste better, which effectively means California can't build more than the one remaining plant. But when I first ran the model with exceedingly low nuclear prices, I turned around and the model had done exactly what I said. It built 16 nuclear power plants in Tijuana. So that's what you get when you put it into a program. It was saying build all the nuclear just out of state, send the power in, so I made a few adjustments so that didn't happen in the model anymore. But what I want to really end with is this, what I hope is a pretty obvious observation. You maybe say I didn't need to spend 20 PhD students and 5 years building a set of models and something that was kind of blatantly obvious, and that was that there's a lot of ways, and let's throw out this one scenario where we're not energy efficient, where we just spend so much more than the other cases. All of these get to that 20% goal. Many of these get there more cheaply than the path we're on now without greening the system. But all of these technology mixes don't tell us what to do. I argue for this one over here. You might argue for this one over here. Whoa, I don't know what I'm doing there. I'm going crazy. But this says that there's a whole menu of options. And to make these options work, you have to think it through. While it's true that many of these are less expensive than the fossil fuel alternatives, they require you to coordinate things. This case here, for example, lots of distributed solar, doesn't work if we don't invest in the transmission and distribution so that it can come online. So that's not a subtle point. Right? We can have a very aggressive solar policy, but if we don't build and make the distribution system work so the utilities are willing to support it, something which they're marginally doing today, but they're not really excited about doing, or build transmission out to large desert facilities, just because the cost in a linear program add up doesn't mean we'll do it. Doesn't mean it'll work out. So for example, the case that requires the least risk of not having the right transmission is ironically the case of nuclear. Because basically if you want to decarbonize a system, even if nuclear is expensive, wherever you have a coal plant today, you have to have enough water there as well. You can take out the coal plant and drop in a nuclear plant, and that's basically what the model does. That doesn't mean it's my favorite scenario, but what this really says is that as clever and as good as we get at the basic science and the engineering, this is ultimately a policy choice. And if we can't coordinate things, we won't get there. Now, thankfully in California, we're quite coordinated. That box I spent all this time describing really shows a system where we're able to get there. But lots of other parts of the world don't have that level of coordination. And California made some pretty significant missteps along the way. We are remarkably fortunate here that California's resource base of solar, wind, biomass, geothermal is so exceptionally good. And for all of the massive fights between the North and the South, between the Democrats and Republicans, we have actually a system today where we can have thoughtful conversations about what mix we want. And that's not something a lot of places can say. So while I'd like to conclude by saying this is a very optimistic and hopeful talk, I believe, because we have this science and technology base to get there, the real worry is if we can't find a way to make this dialogue work better, to make that 100th engineer story the norm, not the exception, even though we're fully equipped to make this happen and actually save money getting there, which is the amazing part of the story, we may block ourselves just because we are so slow and so far behind in terms of having that broader dialogue. And if we can't do it here, with all of the advantages California has, that's a really worrying sign for other parts of the world that have even bigger challenges in place. So thank you very much. I look forward to some questions, and I hope that was useful.
Cool. So, if you have a question, just raise your hand, and I'm going to run up and give you a mic so that everyone can hear you. Cool.
And do introduce yourself so I can know who to track down if it's something nasty.
Hi, I'm Ronak. I'm a senior chemistry major here at Harvey Mudd. And my question has to do kind of with your last slide, where you have a host of scenarios for technological predictions, and then you kind of make models based on that. And I was wondering whether any of your models take into account the impact of certain political or social. I know it's harder to make predictions in that field, but for instance, there's a lot of opposition to many of these industries from people who have a lot of resources, and how you can, or whether you make an effort at all to anticipate the impact of those on technology.
So, I mean, great question. There's no single answer to that because there's so many different pieces. But we are certainly finding a lot of interesting aspects of exactly how we can use models like this, not to predict the future, that's the real fool's errand, but to try to illustrate the different scenarios and how they would work together. So let me show you a version of this picture, and I'm going to take this case here, the reference case, just where the prices are on the trajectories they're on, and give you a snapshot of the energy mix in 2050. This is the kind of plot that power engineers look at all the time. And so what you're seeing here is, whoa, a little too excited there. So what you're seeing here is 2 days a month just stitched together. And so for each month, what I've put is the peak demand day and the average day. And if you put them side by side, you can see the hours of the day, 7 o'clock, 3 a.m., 11 a.m., et cetera, down the bottom. And the black line is the demand. The light blue is wind, yellow is solar, orange here is solar thermal. Here we have natural gas, we have geothermal, that tiny thin line of purple is nuclear. And then we have these negative going spikes. That's the amount of storage that we need in the system. So this is an interesting example of exactly what you're saying. Lots of worry about how we might make these goals happen. In this particular model, just to sort of reference it, what we have is a carbon price. California has a carbon market. Our current price of carbon is about $12 a ton. And what this says is that, again, in this kind of oversimplified computer model, the price of carbon in 2050 is about $55 a ton. So higher than today, but, I mean, not inconceivable by 2050. It's actually less than the cost increases for inflation. But here we have this interesting story. To make this work with solar and wind, we need an amount of storage. One version of the storage is large facilities owned by private companies or utilities. SCE just installed a large one. And another version is distributed in each home. For example, a Tesla Powerwall, or simply a electric vehicle's battery being run vehicle to grid. And one of the interesting conversations we've had, in particular with Orange County's petrochemical and defense-related companies, is there is a huge opportunity to become a leader in this distributed storage if they get ahead of the game. And it's an opportunity to invest. And so what the California Public Utilities Commission, using this model, decided was how much storage should California require in 2020. Now, the amount of storage that we need in 2020 is 0. Because we have a well-functioning system of pumped hydro that we can use today, and we have lots of natural gas plants that will be used less and less over time. So if we don't shut them down, which is a political and a financial decision, those could be our backup. But California is choosing to invest in storage before it's economic to ramp up experience and to ramp up industry that we think we will then be able to sell around the world. So it's a bet on the learning curve, and it's a bet on California being an innovative economy. And that conversation that involved the utilities, it was very strongly, almost half the meetings took place in Orange County at lots of big companies, was all about their ability to transition to become leaders in the storage industry to come. So this doesn't answer your question, but it just kind of illustrates a conversation that the model doesn't solve, but it allowed us to get people at the table. And in fact, the storage number, the requirement, came out of first doing the modeling and then presenting it to the utilities so they could estimate what the cost would be. And the number that was settled on was kind of a sweet spot between what the environmentalists wanted, which is basically we'd like to see 5% of our total generation need available as new storage technologies, and what some of the other companies said, give us a lot more time, and so we settled on 2%. But that was a conversation where the model allowed us to think through and to get some unusual parties together. Rockwell, Bechtel, and others got excited about it because they think they can be big leaders in storage. And storage doesn't just mean batteries. It also means flywheels. It means all kinds of different technologies, flow batteries, batteries with almost unlimited number of cycles without degradation, came up as exciting areas where California companies think they'll win. So, great question.
So you brought up a few times the idea of like the 100th engineer who understands the non-technical aspects of what they're doing. And I wanted to see what you thought about where that kind of a person is like most needed right now in moving towards a clean energy future. Like what roles need to be filled, having an impact there.
Interesting. So great question. I don't have an answer. I mean, where they're most needed, where they're most likely to go because it's exciting, is probably not the same thing, right? Because you guys, as you graduate, make those choices, and I probably get asked a couple times a day, what technology would I go into? And I almost never answer it by saying, you should go into solar, right? To my mind, the area where we are most lagging is this interface between the technical models and behavior. And by behavior, I mean everything from policy to how to incentivize activities. There have been some really interesting new companies that have emerged that have basically sold behavioral strategies. There's a company called O-Power, which is the first large-scale company to find ways to incentivize energy efficiency. And what O-Power did to an engineer looks so simple as to be embarrassing. But it was so interesting. What O-Power basically is, you sign up for their service, they'll analyze your energy usage, they'll tell you which devices you have that are efficient or not efficient, and then what they will do is they will compare you to your neighbors. And it turns out that while humans are not really that good at absolute assessments of how am I doing, we're really good at knowing are we better or worse than our neighbor. And we're really fixated on that. And so a mapping tool, this is one that our lab built called Cool Climate Maps. This is you can do on your phone or whatever else. And let's see if I can operate it on the screen. Not so well. This is just because I'm much klutzier than you guys at doing this. And it's slow to refresh. Let me see if I can get it to do its thing. So this is if you would, okay. It's a national map. And what you see here as you move the cursor around, it's showing the average emissions in each zip code. This is averaging over homes, not industry. But it shows the average in each area, and it shows it broken down from these different categories. And of course, the first thing everyone does is put their own zip code in, right? So I shouldn't be on the East Coast here, I should be out in California. But here we see this interesting picture, and as you go past, what are these little reverse pimples? They're cities. Because for the same income level, living in an expensive urban area, you typically have less square footage, less lights, less hot tubs, less marijuana grow lamps, whatever your usage might be. And so urban dwellers are typically lower emission for the same level of income because they're spending more on rent and other things. And so we have all kinds of interesting details that says we have to compare. There are some parts of the country where the data is not so good, but we get out here to where the data is good. I'm not sure I can expand this without blowing it up too badly here. But the first thing we found was that getting in here and looking at why were some zip codes higher than others, having good high or higher speed rail or commuting makes a big difference. Urban areas that are really affluent have higher emissions, and if I can scroll this down, I think I just put the New York City version on here. So here is a version on the Atlantic, on the eastern seaboard, and if you look closely, you will see this green line, which is what? That's Amtrak. People that live close to Amtrak have lower carbon footprints than others because they do more of their regional commuting on it. And then if you look in more detail here, you see there's New York City, lower carbon here, but it has this big carbon shadow around it, right? Lots of cities in the United States have earned wonderful awards for being a green city, in general, by defining the suburb as someone else's problem. That's cheating, right? And we're no different in California, but I happen to have the graph here for the East Coast. And so New York City, which wins award after award, conveniently defines New Jersey and Long Island as someone else's problem, even though the economic function of the city is highly dependent on those suburbs. So this interface between the science, the opportunities, and using this kind of information. So while I was very snide about economics as a physics undergrad and grad student, I would certainly say that learning big data, learning behavioral economics are the kinds of areas where that 100th engineer can really augment what they're doing and just find all kinds of fascinating projects that you might work on. So only a partial answer.
Hi, I'm Grant. I research solar here at MUD. And first question is particular to your best case scenario or your happiest scenario in that final graph. Favorite, obviously with solar growth and low-cost batteries. Is that with predictions using silicon-based solar, or is that with advancements in thin films such as perovskites?
Yeah. So it's a great question. So the graph I didn't put in, because I thought I wouldn't get to it, would be there's a graph that the National Energy Lab puts out each year, and it shows the evolution of each solar cell type. And so it shows the maximum efficiency of each type of solar cell, crystalline, thin film, quantum dot, all the fascinating different areas. And there's been this long-standing battle. It's not unique to solar at all. And it's, will the exciting upstart displace the incumbent? The The idea that hybrid vehicles would ultimately displace internal combustion vehicles is one where California played an outsized role in pushing hybrids into the market through our ZEV, or zero emission vehicle mandate. But as hybrid vehicles came into the scene, and lots of people like in this room in the Bay Area bought them, internal combustion vehicles got more efficient too. So the baseline was improving, and so while going to a hybrid was great, the delta was smaller and smaller because internal combustion vehicles were better and better. What's interesting is that another case like that, compact fluorescent light bulbs, the energy efficiency community has spent 20 years making the case that we have to get off incandescence onto compact fluorescence. And there was economic argument after economic argument why it was so much better to go the compact fluorescent. We're going to save all this money. And a story that lots of us love to tell is that analysis of, CFLs are so much better, we all are idiots by not installing them, that all assumed things like, because they last longer and they use less power, they're going to save everyone tons of money, we're all going to buy them. Well, that assumes that when you move, you take your light bulbs with you, right? That's a pretty basic feature. Now, there are some eco-warriors that do, but most Americans, even if they buy a light bulb, they don't take them with them. So we have these examples of a technology that everyone thought would have taken over, and they didn't. Now, we look back at CFLs, and we say, that was interesting, but it was a transition to LED lights. Well, 20 years ago, that was not the conversation. The conversation was LED lights are so expensive, they'll never be a big part of the story. We've got to get everyone onto CFLs, and all those nasty homeowners and Republicans and things who don't buy CFLs, they're just dragging us down and they're stupid. Well, that was wrong, right? So this push towards the cleaner technology option is a really complicated one. The movement from internal combustion engine vehicle to hybrid, now maybe leapfrogging that to electric vehicles, all of these are examples of where that opportunity to push far ahead comes in. So solar is a perfect example. When solar wasn't part of the market, everyone said we've got to get onto solar. And the solar research community, the physics, the applied physics, chemistry community 20 years ago was almost entirely focused on crystalline traditional solar panels. And I have quote after quote from my good friends working in the lab saying, thin film on these things, these will never be important. They're cute, they're niche applications, they are just not part of the mainstream. Now, thin film is routinely installed, but at the same time, traditional solar has gotten better. Gotten less material, it is improving. So the baseline's getting better, and the real question is, does the timing of bursts of interest, like that $100 billion we spent under President Obama in the stimulus package, did that lock in a generation of solar panels because those were available at the time? Not that they were the optimal or that we want to keep an evolution going. They were available, the money had to be spent, they got it. And now quantum dots or perovskites come along and we all think they're better, or some people think they're better, but the market is gone. Right? Some people think the same thing for electric vehicles. Tesla did an interesting job, maybe good, maybe bad, but they blocked everybody else. That's one of the arguments, and we'll see. And so this evolutionary story is really hard. I am of the view that thin film ultimately makes much more sense than crystalline solar because of the massive reduction in materials. And what you give up in efficiency, you more than gain in the life cycle improvements. But former Berkeley professor Ike Weber, major figure in crystalline solar cell research, now just retired after 10 years of heading Germany's largest solar energy research institute, thinks the opposite. He thinks that traditional crystal cells will just get better and better. Everything else will be in the margin. I disagree with him. He has more experience. We don't know. Long answer. I could have said we don't know 5 minutes ago, right?
Hi, I'm Andrew. I'm a physics major at Mud. I have a question about natural gas. You mentioned it as a transition technology. So you build something now, you need to know that it needs to be gone within 50 years. How do you see that playing out, and how do you see the conversations around fracking in the United States right now play into that?
Okay. So using the switch model again, this is the impact of gas in the West. In our modeling scenarios and in many of the other groups, gas plays a dominant role, not in California, but in all the West by 2020, 25, up to 2030. Then the renewables really kick in. But here is an interesting piece of the story. So let's say we really take our carbon cap seriously, which you can argue maybe we won't if it gets too tricky. This is California's carbon budget, our 2020 budget, the reduction we need to go 2030, 2040 to get to our 2050 total 80% down. And the black is gas. Then we have, the black is coal. Then we have gas, combined cycle gas turbines. And the red is the amount of gas that leaks. So no economic value at all, just simply leaking into the system. And because there is a massive political battle over what is the leakage rate, it's not the same for every gas field. Are fracked fields higher leaking than traditional ones? There's people who argue both ways. I think they are higher, but other people say, no, they're newer, so they're less leaking. There's a whole bunch of arguments. So to avoid taking a single stand on it, what I've done here is I've plotted the energy mix of fossil energy as a function of the leakage rate. Couple landmarks. The US EPA's official number is the leakage rate is 1.5%. I think that's dead wrong, but that's the official EPA, no offense. Rich Howarth, a researcher at Cornell, thinks the leakage rate is between 8 and 10%. I think he's also probably wrong. An amazing guy at Stanford named Adam Brandt has done a large-scale study with NREL and a number of fracking companies, and he finds that the leakage rate is generally between 2 and 5%, but that a few super emitters dominate the landscape. So not a simple story. But look what happens. If the leakage rate is 0, then no surprise, you probably bring more and more gas into the system at the expense of coal. So coal goes away. But as the leakage rate goes up, there's a crossover point where coal on a greenhouse gas, not water, not particulate basis, but coal is better than gas, turns out to be about 2.5% leakage rate. Coal is now better for the environment than gas. So should you build gas plants, if we take the cap seriously, which maybe we don't, I think we should, but that if the leakage rate is about 2.5% or more, then we should not push to gas. We should actually use coal judiciously and phase it out. That is a controversial statement to say something. And look what it says out here. Let's say the leakage rate is 2 to 4%. Out here, the red is the leaked gas. Well, that says that even by 2030, let's call it 4%, just to give me a little room to wiggle here. This says that roughly half of our entire greenhouse gas budget would have to be used to account for gas for which we're just leaking. Now, nobody wants that, right? There is an interesting out, and that is that leaking gas is probably one of the more easy things to fix. Better well casings, a whole variety of features, better gas line, Teflon coating. There's a variety of things you can do. You could probably bring that leakage rate down. Will we bring the leakage rate down, or will we say, oh, this leakage issue, this is annoying, this is somebody else's problem? I would bet for the latter. When the city of Berkeley passed its first greenhouse gas law and was really serious about it, and then an engineer pointed out that there is Highway I-80 that passes through Berkeley, and if you actually take the account of the emissions in that short section of I-80 through Berkeley, that was half of the city's emissions. City council voted to define I-80 as the state's problem. Well, not everyone can define it as someone else's problem, but I would bet that this really tells the science story of gas, but we will probably find a lot of ways to minimize this politically, because who really wants to spend all their energy dealing with the leakage issue? So great question.
So for the sake of time, we'll take 2 more questions. Anybody?
Sounds like we're exhausted. Always count on an ergie to...
And this is fantastic. So what about those those students who in the room, and I know there are some because I brought them, who aren't engineers? What would you say to the 100th social scientist or historian or
So as much as
other
it
group
pains
of-
me as a physicist, I actually think that this story is in your hands, not in the scientist's hands, right? Because I think this is just one example of the degree to which we make it or not because of social institutions. Whether we need more innovation on the science side, I think no one's going to disagree, we need to at least progress. But there are plenty of arguments and analyses how to meet our climate targets, sustainable water targets, et cetera, based on existing or foreseeable near-term technology. I don't think that's the hard part of the story. I think the fact that we have marginalized social sciences and the humanities, every large project that we do on the energy side typically is 90 or 99% based around the science, the engineering part of it, and maybe there's a little bone thrown to the social sciences at the end, or maybe there's a social scientist employed to kind of study the process. I was involved in a $500 million biofuel project, which is not trivial size, and at the last minute, the social scientists were elated and the engineers begrudged spending $5 million out of $500 million to understand the impact of biofuels. And we know today that the story of biofuels is entirely driven by impact, not by what is going to be the best enzyme to get the best laboratory ethanol or other technology. So I actually think that unless we can figure out a way to reverse this equation and actually to put thinking about the impacts in the front, that all this cool stuff that we could use to deploy to get there doesn't get us there. So that's not a prescription of how to do it, but I think it's my best argument for why we must do it. Right? 1968, famous address to the AAAS, the Association for the Advancement of Science, by Garrett Hardin, who was the president at the time, a controversial figure. His argument, a famous paper published in Science, he argued that the hardest problems we have are not technical. And yet we look at them technically over and over again because the parameters, the boundary conditions are the most clearly defined, not that that is actually how we solve them. And so starting out and thinking about what we want and what the distributional impacts are, I think we have to get there. So I am elated that California has probably pushed the envelope further than it needs to, but I am delighted that California's new climate law, not Assembly Bill 32, but Senate Bill 32, actually requires us to massively attend to the equity and environmental justice aspects of the story. The bulk of the money from our cap and trade system, the bulk of the locations targeted are those where the environmental justice issues are the largest. Does that mean we will do it right? I will see, but it is at least an acknowledgement in California that this actually has to be how we now shape these policies. And yet we know that our history of policies, right, every incentive we have for solar or for electric vehicles is all based on the richest get the largest share. The incentives, the rebates are all proportional to what you spend or what your income is or the fact that you own a home or own a roof, as opposed to what's starting to emerge. Now we have a new bill, still with some imperfections, called the Solar Gardens Law. And what that says is that rooftops in urban areas need to be made available so that people who don't own their home are able to offset utility bills by having a share of that shared rooftop solar. That is far from perfect, but it's one example of, after many years of thinking about essentially the capitalist first approach, we're thinking about a more distributional one, right? So my favorite, I think I said it when you took ER 100, my favorite, or maybe my saddest joke, is that it remains the case in the United States, not just in energy, but certain energy, but certainly in the energy field, that what we clearly have right now is socialism for the rich and capitalism for the poor. And we have to reverse that, because that is not the way to build an equitable energy system. And if we just solve the climate problem with energy, we've failed to take advantage of lots of the interesting distributional benefits. Smarter cities, better urban transit, better air quality where poor people live. There's lots of interesting aspects that looked in the past like interesting side notes to the sustainability transition, but I'm hoping we're beginning to recognize these are actually where the action's at. And these are all social science, humanities, legal, policy questions, where technology is important, but it's the tool, not the answer. Great point.
Any final questions before we wrap up here?
I want to thank you all. I really appreciate the chance to have this conversation.